São Paulo. She will talk about fresh look at finite size effects in majorana systems.
Tô certo aqui? It's this way. Okay. Hello, everyone. I would like to first thank the organizers for this opportunity. And as you can imagine from the title of my talk, I will speak about something completely different from whatever people are talking about here. But in the spirit of the workshop, and inspired by Bill's talk on Monday. So Dennis and I chatted a little bit, and we sort of, we don't have a concrete idea yet, but we are trying to combine whatever I'm doing related to Majorana's and what he is doing with NEV centers. But when we were chatting, he pointed out there is in fact one proposal, this one, in which they have a 2D Rajba system in which they induce superconductivity, and on top of this 2D system, they place magnetic impurities. And they, so there is a coupling between like the Rajba system and the magnons here. And what they show here, I'm not gonna go into the details here. It's just some kind of motivation for this, for some future work. But what they show here is that, for example, they calculate this is the spin expectation in the z direction, and they show that when you are in the topological phase, you have this kind of behavior, and then they sort of engineer a trivial state, is a zero energy state as well here, and they see that when they calculate the spin expectation value, there is a difference between the topological and the trivial phase. So this is the kind of signature that would indicate that you have or not a Majorana. And this is different. I'm going to talk a bit about this. This field is very controversial. And the measurements that at this point, people are looking at, which is the conductance, the zero bias conductance. Well, you cannot really distinguish between trivial and true Majorana modes. So this would be another way of showing that you have or not Majoranas in the system.
What is the meaning of P equals 0 and P equals 1? P equals 0 and P equals 1?
I didn't go, this was added yesterday, so I don't know the details. But as far as I remember, this has to do with the ground state of the system. Because in the case of the Majoranas, it's degenerate. So I would like to acknowledge, so the work I'm going to show here was done in collaboration with Rodrigo, who was just finished his PhD, and with Carlos. And I'll talk about two of our recent works on Majoranas. This one is, so the system is the usual three-terminal wire. It's a semiconducting nanowire in which you have all the ingredients to mimic the Kitaev model. And in principle, you would see signatures of the majorana modes here. And the more recent work, this was sort of just accepted at PRB. We just received a very good report, so I'm saying that it was accepted, but it's almost there. So this other paper is based on this new proposal in which they have the wire, but now they have gates underneath the wire, and they define quantum dots. And this is really similar to what, so these are what they call artificial Kitaev chains. This is a very busy slide, but it's just to show that there's been a lot of work for many years on majoranas. And for people who are not in this, most of you are not in this business, why majoranas? So later on, I'll show the Kitaev model, which is a toy model in which you can really see what these particles are. So these would be used to build a topological quantum computer. So that's why people are interested in these particles. Well, you all know that Microsoft is, I think, the only company that is investing a lot of money trying to find majoranas and build this topological quantum computer. So the first, one of the first measurements in these systems, so this is a nanowire in which you have spin orbit coupling, you have induced superconductivity, S-wave superconductivity, and then you have an applied magnetic field. They measure the conductance here, and what they see is a zero bias peak here. It depends on the magnetic field. So this was not, this measurement was not conclusive because many other types of phenomena can give rise to a zero bias peak. So a bunch of them are here, like the Kondo effect, disorder mainly. So it's the main problem right now. And Andreev bound states, etc. So around this time, we have this work, which is, it's a bit, the geometry is a bit different, in which you have the wire, but then you couple a quantum dot to the wire. Here is the Kitaev chain. And then you measure the conductance through the dot. And what we observe here is that the conductance, when you are in the topological phase, what you see is this plateau here. So this is as a function of the level of the dot. So you can push it below the Fermi level or above the Fermi level. And then what you see is this plateau here in the conductance, and its value is different if you had like a resonant level, like a normal quantum dot. So the value here is like a half of what you'd have for a normal mode. And I want to mention that this is the kind of, in these artificial Kitaev chains, this is exactly what they are doing now. So they are coupling, so they have the Kitaev chain, and they are coupling a quantum dot to try to probe this zero energy mode.
If you are in the Kondo regime, you also have a plateau of the conductance, right? So, but I think it's at the one, not the half.
Sorry?
Yeah, in the Kondo regime, you also have a plateau in the conductance.
I think if you are in the Kondo regime, there is another work that took into account the Kondo effect. And but then the conductance is different.
It's different.
You have like I think the Majorana contributes with half, and then you have a 1 coming from the Kondo.
One, yeah.
It's just one half, right?
Mhm.
Three halves. Yeah,
Ah, okay.
yeah. So
Okay.
it's different.
Mhm.
So after this first experiment, then people tried to look at so this was measuring the local conductance. So after this, people tried to come up with other ways of seeing the Majoranas, and then there are a couple of theoretical works suggesting that you can use the local conductance to probe to see the zero bias peak, which is a signature of the Majorana, and also use the non-local conductance now to see that you have a phase transition, like you're going from a trivial to a topological phase. So this is what Microsoft did when they proposed their protocol in 2023. So they are using these two measures to say that they are seeing Majoranas. So I'll just briefly introduce the Kitaev model. So people who don't know the model can appreciate it a little bit. So you start with, this is a toy model in which you have like an on-site energy. So it's an spinless model. You have an on-site energy, you have hoppings, but now you have a term here that is not the usual superconductivity, it's P-wave superconductivity. So in which you pair electrons with the same spin. And this was proposed by Kitaev in 2001. And if you just simply do this transformation here, you just write now your operators for fermions in terms of what we call Majoranas here. And Majoranas have this property. I didn't mention this before, but this is something different between fermions and Majoranas, that the usual commutation relation is different because you have something, they are there, the particle and antiparticle are the same thing. So this is purely mathematical. So if you rewrite this Hamiltonian in terms of these entities here, you end up with something like this, in which you are coupling all the Majoranas. But then there are two regimes in which, let's say that you put delta and t to 0, and then you just kill these terms, and then you just have this one. So what you end up with is just a chain. So the sides are not connected to each other, but they are connected within the sides. And this is the trivial phase, in which you have just one ground state. And I also should have mentioned that what is why Majoranas can be used to for topological computation is that a feature is that the ground state is degenerate, and now you can use a ground state which has no particles and just one fermion, the non-local fermion, as your qubit. So these are the two states that people use for the qubit. So the other regime of the Kitaev model is when you now put mu to 0, and then you choose delta equals t. So in this case here, you just kill these terms, this term and this one. And what you see here is that you end up with a chain in which there is coupling between the sites, but between one of the majoranas and the other one. But these two here are unpaired. So if you go back to the fermion annihilation and creation operator, then you have this Hamiltonian here, but you see that these two here are unpaired, and you can write it as a fermion, but this fermion doesn't appear in the Hamiltonian, so this has zero in it. It doesn't cost anything to add this fermion or not to the system. So then you have the degeneracy of the ground state. And here I'm just showing the Kitaev model. What happens? I just diagonalized the Hamiltonian for here for different numbers of sites, and you can see that so there is a relation between mu and t when the gap closes, and then you see these states appearing in the gap. So these are the majoranas, and if the wire is not long enough, they hybridize, and you see these oscillations here. And the other feature of majoranas is that they localize, as we saw in the previous slide. So the two majoranas at the ends of the chains are decoupled, so they localize at the ends of the chain. So what we tried to do was we are still doing here conductance measurements, but we tried to do something different from what people were doing. And we asked ourselves whether we could use only the local conductance to distinguish between trivial and topological states. So I'm using, so this is, the system consists of the nanowire, and then I have the leads, and then there is coupling between them. And then I'll measure the local conductance is measured, it's between, for example, the left lead and the superconductor.
Before we go to the next page, what's the difference between first line left and right?
First line, this one and this one?
Yeah.
So,
why is it separate?
So this one is just the, so I just took my continuum model and discretized it. So this terms, the hopping term comes from this kinetic energy. And then I also have a chemical potential here. I'm just adding this U here, is just because I add disorder. And then this is the Rajva term. This is superconductivity, and this is the Zeeman term.
Yes,
yeah.
Thank you. Just because I needed more time.
Okay, yeah, sure. So the idea here is to play. Oh.
One more question.
Can you repeat, please, what is U, and again, where is the Rashba term?
The Rajva term is this one.
Yeah.
This is the Zeeman term.
Uh-huh.
And this U here, I'm just adding to this. I'll add disorder to the wire. So
okay.
in principle, this is just to take its disorder into account. It should just change the chemical, the on-site energy here.
So I get that now the superconducting term is it's on site, the superconducting pairing. Because in the previous slide it was like.
Well, this is the wire. So the Kitaev model is spinless, but this one is spin full. So this is the usual S-wave superconductivity. So I'm coupling up and down spins. And this is encoded here in the spinner, in which I have C and C.
Okay, so psi is the spinner.
Yeah,
okay.
yeah, exactly.
No,
yeah.
Now I can understand.
Yeah, I should have written somewhere there. But the idea here is to now play with the barriers here that change these gates here and either raise the barrier or lower it and see what happens in the system. Here is just to show this is the spectrum of the nanowire, which is similar to the Kitaev model. But here the parameter we vary to see the phase transition going from trivial to topological is the magnetic field. And here you can see that when you are sitting here on top of the zero mode, the wave function is localized.
Poliana, why do you say that this PC squared gives you the probability of have majorana at the boundaries?
Which one?
And the PC squared, it's high at the border of the system, right?
You mean it's? I mean it's
Yeah,
localized.
It's localized at the
yeah,
end.
at the ends. Yes.
But I cannot say that they are just electrons there, or they should be majorana.
Well, it could be that this is what. That's why people cannot distinguish between trivial modes and majoranas, because you can have modes in which you have they are localized at the edges. I mean, people have engineered these modes to look like this. So yeah, in this case here, this is purely, let's say, theoretical, because I know there was a phase transition here, and this is a majorana in this case here. But in an experiment, it would be difficult to distinguish between something trivial if you have it localized at the ends of the chain.
But this PC is the wave function for electrons, not for
Yeah,
majorana,
for electrons. Yeah, yeah, yeah.
Well,
everything like so majoranas you cannot really they don't have like an
Okay.
occupation number or anything like that. But I can also have like wave functions for majoranas. You can always go back to the fermion description.
Okay. One more, just a minute.
Yeah.
So you're plotting against the Zeeman term, and is this for finite U, which is the
Oh no,
degree?
this has no disorder.
Oh, so this
Yeah.
U is 0?
No, this is pristine. Yeah,
Ah, okay.
yeah.
Right.
So I just chose some parameters for the chemical potential and etc.
So this is more like a figure of merit, because
Yeah, exactly.
for U equals
Yeah.
0, that's what we expect.
Yeah, exactly.
and-
Yeah.
Okay.
Yeah, this is the pristine nanowire.
Okay.
So the question we want to answer is, can we use only the local conductance? So as I said, I'll play with the barriers here, and I'll just lower or raise the barrier. And here what we calculated is we are interested in the differential conductance. More specifically here, I'll talk about the zero bias conductance. I'll start with T equals 0 and show the results, and later on I'll show some results at finite temperature. So here there are three processes that contribute to the conductance, and are the local undriven reflection, crossed undriven reflection, and what I'm calling direct tunneling here, but I think some people call it elastic cotunneling. But the most important process here is the local undriven reflection. And we can see if I plot each one of these processes here as a function of the magnetic field, we see that before the transition, we don't see none of the processes are contributing when you have majoranas here. And then after the transition, then you see that LAR is the the process that contributes the most. These two terms, it's easy to see if you are working with an effective model, a low energy effective model, that CAR and this direct tunneling are proportional to this hybridization energy. And that's why you see, when you see this, the LAR going down here and the two other processes going up here, is this is due to when I'm somewhere here, and when this splits, then I'll have like a contribution, a larger contribution for CAR and direct tunneling.
In here, are we using the Markovian limit?
Oh, yes.
Is it easy to go away from the Markovian limit in this theory using the non-equilibrium Green's function, forgot the name?
Keldysh?
The Keldysh formulas, yes.
Here we use the scattering matrix, which I believe does not take that into account, but I'm not sure, to be honest.
Mm-hmm.
But I
the
guess
reason I ask is, in a similar but not the same, it wasn't continuous. In a discrete system that I worked with in 1D with the leads in both sides, I remember in that result, the Markovian limits refers by showing the mapping between Markovian, non-Markovian, the Keldysh and non-Keldysh. We could show that the Markovian limit means a chemical potential for the leads being very large, going to infinite. So I either
okay.
could have the one side and the super high chemical potential or very low chemical potential, and you can play with those limits. But in the Keldysh formalism, you could relax that, so you can continuously change the chemical potential of the leads.
But
so my question is whether here you also allowed to tune the chemical potential freely?
When you say that you're changing the chemical potential, like, I don't know, increasing it or...
Right, yes.
Yeah, but here I'm only interested in the case in which the difference between the chemical potentials here is, like in this case, between the superconductor and the leads is small, because I'm working at in the linear regime.
Mm-hmm.
Are you referring to this, or?
No, not sure. Not
Okay.
sure. But I'd like to discuss further
Okay,
later.
yeah, sure.
It's very interesting.
I think you are considered the wideband limit.
Yeah,
For
it's
the
the
leads.
wideband.
So
Yeah, it's energy independent here
Yes, so
when I
it's
take the leads.
basically a Markovian approach. Right.
So this is just to show how the process here for the specifically for the local undrive, how they vary with the magnetic field. So here we see that before the transition, it's the usual up and down spin undrive reflection that contributes as usual. But then once you reach the topological phase, now you have more process like same spin undrive reflection. And here is just to show how each of these processes vary with when I'm varying the barriers here. So what we find here is that if you are so measuring the local conductance, GLL and GRR, what we see is that in the trivial phase, so I'll focus on these three lines here. What you see is that when you lower or raise the barrier, so on the left side, what you see is that the conductance is constant for the trivial case. But then if you measure GRR, what you see is that the conductance goes to 0 quite fast. And then,
One moment, please.
In both plots, what are these decaying lines? The
so here,
yellow and
I'll
purple.
talk about them. These are the topological ones. So I'm first focusing on the trivial phase, just to show the difference between the two. And in the trivial phase, you see that there is no correlation. What I'm trying to show is that in the topological phase, there will be a correlation between the two sides. But in the trivial phase, so the conductors behave completely different on one side and on the other. So you see that I'm now lowering the barrier here, and the conductance on the left side is going like it's a constant. And then on the other side, because you are raising the barrier, then the conductance goes to 0, as we would expect. But then in the topological phase, when I do the same kind of thing, like raise the barrier on the right side, what I see is that they are correlated. Like on the left side, they have the same behavior on the left and on the right side. And here we have different values for the magnetic field. And the curves are different exactly because when you have, let's say, this curve here at this specific magnetic field, you are sitting on a point in which the energy, there is no hybridization energy. And it should go to the limit when the hybridization energy is 0, then you'd have what you should expect is 2e squared over h, like it should be 1 here, if you have a true majorana sitting at the 0 energy. And then we also sort of based on this paper here, so we engineered a trivial mode that would behave like majoranas, but then we put so the Rajba constant to 0 and the magnetic field to 0. So it's a trivial state. It's a trivial Andreev bound state to see how it behaves here. And what we see is that it behaves as a trivial mode. So on one side you have these dotted lines here, and on the right side it simply goes to 0. And as I said, if you had like true Majorana 0 modes, then you'd have on both sides this conductance here. I should say that in this raising the barrier here, this hybridization energy plays a role, because then we can see this correlation between the two sides. And to test whether this was really robust in a way, we did simulations. So we added disorder, and for the trivial case, we see the same kind of behavior. Now it affects the value of the conductance, but you see that they are not correlated. But for the Majoranas, for the topological phase, I'll not say Majoranas because they are not true Majoranas, but for the topological phase, you can see that there is a correlation between the two sides. And this we can see this by calculating the density of states. And what we see when we change the barriers here is that, so this is the symmetric case. So you see that around 0 energy, you have some spectral density here. But then as you raise the barrier here on one of the sides, then you have like sort of a gap here in the density of states. But on the right side, you have some enhancement. So the weight of the spectral function here, it's stronger here. And then this is why the conductance on the left side at some point goes to 0, because then you're losing this spectral density here. But then on the other side, as for a trivial mode, if you are raising the barrier, then the conductance should go to 0. But then since you are enhancing this part, this spectral density here around 0, then you have some remaining conductance, let's put it this way. And this is correlated between the left and right side. And now if I add temperature, then things, of course, get...
Poliana, one question here. Mariana?
Sorry, it's going to be my last question.
No, it's fine.
So can you, just because it's about the previous one.
This one?
So what's the significance of this? Is this, does this strengthen the argument that these localized modes at the edges are majoranas, or the opposite? When you, because okay, I see that the symmetric case gives this well localized states,
Yeah.
etc. So it's a strong indication of
Majoranas.
localized majoranas. But this unbalance and this gap opening, what's the significance of this for the argument?
This is actually just to show that why, what you'd expect if you raise the barrier, as I said, is that the conductance goes to 0. You cannot tunnel between the lead and the wire. But then because you have something like this enhancement on the right side at 0 energy, where I'm looking at things, then the conductance behaves in a different way. So this is not what the density of states for trivial states look like. Because once you start to raise the barrier, then you start losing spectral density here. For
so
both
these two things
sides.
would be like, they would, if it would be a trivial state, so enhancement of the barrier would connect to
then you would not see
correspondent
anything like this. No.
loss in the spectral weight.
Yeah, exactly.
But you're seeing the opposite.
Exactly.
Okay.
Yes.
And therefore,
just because
it's
these
something non-trivial.
sorry.
And therefore, it should be something non-trivial.
Yeah, we believe that this is due to the fact that the majoranas are coupled, because there is some kind of hybridization energy. Then you can see this coupling between the two sides.
So that the loss of spectral weight is being transferred
Well,
to the
not
other
to
side?
the other side, no. But this is like since it's connected to the lead, it's like the majorana is leaking to the lead, something like that. In this case here, but in this case here, it's not possible. So it's getting, let's say, more localized on the other side.
Okay. No. But then if it's leaking into the lead, you should look for it in the lead. With some probe, something that indicates that, okay, it leaked into the lead.
This is I'm telling you that this is what's happening based on when I showed that that system in which you have the Kitaev model, and then you couple it to a quantum dot. What we see, like even if you can look at the density of states as well.
Of the lead.
No, there I have the dot.
Okay.
So the dot here is sort of playing the role of the lead here. But there you can see that the majorana leaks into the dot, because there is you plot the density of states in both cases, like for the first site where the majorana was before, and then for the dot, and you see that before there was no spectral density around zero energy, but then afterwards, when you connect to the wire, then you have some spectral density there, because the Majorana is leaking.
So
to
you're
the dot.
drawing this knowledge
Yes,
that you
exactly.
to,
yeah.
to this picture,
Yeah.
but there you have a lead.
Yeah, it's different. Yeah.
Yeah.
Yeah,
Okay.
there I can probe the dot.
There you can probe
Yeah,
the
yeah,
dot.
exactly.
Yeah. Okay. Thanks.
So if you now add temperature effects, what you see is that, I mean, if you go to high temperatures, of course, everything breaks down. Because for this to work, and you have a correlation between left and right sides, you have to have like the hybridization energy has to be the most important energy scale. It has to be bigger than the than KBT. So this is a an, let's say, unwanted effect in the system. So Fabrizio said that I have 5 minutes, so I'll probably not be able to go into the details here, but I'll just briefly mention what this is about. So now the new experiments are really trying to simulate the Kitaev chain. So they have like quantum dots. It's a small chain. Right now they are at I think they have 3 sites. So it's the most recent paper. So they have like quantum dots here. And then in the middle, they have a superconducting section of the wire. And it's possible to show with, so they showed with this simple model in which the superconducting part is represented by these 2 Andreev bound states. And then these are just the left and right dots. And then you couple everything through tunneling constants. Then you are able to derive, so you integrate out the superconductor, and you end up with a Hamiltonian that connects the 2 dots. And you end up with something that looks like a superconducting term, and something like a hopping term, which you can compare now with the Kitaev chain. And the experimentalists can actually tune these parameters in this system. They have more control of the parameters, and it's easy for them to tune this delta and t now. So, and this is essential here because what you want is to go, as I mentioned, to that sweet spot in which you have some kind of on-site energy, but then you can tune delta equals t and see Majoranas. So there is also this proposal with this more microscopic model in which you have the dots, you have a Zeeman, you have the possibility of hopping in which there is spin flip. But they all come, you can draw the same conclusions from this model, that you have a term that is connected to this hopping, which is the elastic cotunneling, and the delta, which is connected to car. And what usually people use here in this business to characterize whatever they see is the degeneracy of the ground state. And here we associate this degeneracy with the Bogoliubov operators, and this is connected to the statistics of the Majoranas, which is different from fermions. So the Bogoliubov operators are, if you rewrite everything, they are given by this expression. And the other way of characterizing Majoranas is the Majorana polarization. So this measures how localized the Majoranas are. And if you have Majorana 0 modes, then you'd have something like gamma square equals 1 and Majorana polarization equals 1. So in this work, what we are trying to do is to see what happens when you start to adding more sites to the chain. Because in the system they have now, which is the 2-Kitaev chain, so you have a sweet spot. But then if you move away from the sweet spot, then you are no longer seeing Majoranas. And then what happens when you increase the size of the chain? So what we see here, if you go, this is just 2, 3, 5, and 9, that you are going through some region now that we call topological islands, in which you don't have to fine-tune your parameters. If you are within this region here, it behaves as if you were sitting at this sweet spot. And you can see the same behavior in the Majorana polarization. So here you have 1, and then as you increase the system, then you start to have some kind of island here. We also did a simulation with the spinful model, and the qualitative results are the same. That's what we observe. So when I said about the probing Majoranas through the statistics like gamma square, what we see here is that if you are sitting on one of those white regions, this is going way above the 9 sites that I had there. But then what you see is that if you don't know how to measure this, but then you'd have, if you plot gamma square as a function of the parameters, then you would see a plateau here, which would say that you have Majoranas. And in this work, we actually use now the Kitaev chain and couple it to the dot, just like I said before. And then we can correlate the conductance through the dot to this gamma square. So when you are on a sweet spot or inside the topological island, you see that gamma square is 1. Here it's just renormalized. And the conductance is now that value 1/2 of the E square over H. So, and this is exactly what sort of what they are seeing in the experiments right now, when they increase the chain to 3 dots, and they use a dot to probe how the Majoranas localize. So, thank you. I'll just leave my summary there.
Okay, so I think we have time for only one question. Yeah, okay. No? You are okay.
So just to highlight the fact that no one has ever varied the ratio of the barriers. Are
No.
all
it's
experimental
Mm-hmm.
and theoretical.
Yeah, this is a new thing.
Yeah, I just wanted to
Okay.
emphasize that because I think this is one of the main thing
Yeah.
here, right? So no one, every single experiment, every
Yeah.
theory paper.
I mean, usually you have some, the barriers are not at the same height, usually, from the start, but nobody varied the barriers.
Yeah.
And this is something that Microsoft could incorporate in their protocol easily.
And this three-terminal geometry is exactly the same as Microsoft.
Yeah, exactly the same.
So yeah,
yes.
I'm just emphasizing for the lay person so
okay.
that it's nothing really. But then the results are different in the
Different,
sense
yeah.
of a correlation. Okay, so
It's 2 different things, right? Change the just to be sure I understood, the 2 different things is changing the chemical potential is one thing, but changing the coupling strength is a different thing.
Yes, exactly.
What-
the chemical
what
potential
was-
is kept like, I'm in the linear regime, So I'm
Right.
keeping so there is some kind of a bias between the leads,
Yeah.
but I'm keeping that constant and then varying the barriers.
Right. The
Yeah.
coupling strength.
The
I can
coupling
say.
strength,
Yeah.
yes. Yeah.
Right. Okay. Thank you.
Okay, so on the, yeah.
But here, I guess the finiteness of the chain is crucial to get that
Yes.
left and the right to be.
Exactly,
So
yes.
here you're not probing majoranas per se.
No, yeah.
You're probing the phase.
Exactly. That's what I mentioned at some point, that they are not true majoranas. They are like
They're electrons.
yeah, exactly.
Okay, but so if you make the chain longer and longer, eventually
Yes.
you'll see the asymmetry.
Yeah,
in your
exactly.
conductance.
Yes.
So let's thank the speaker again. Oh, I think.
So let's discuss what